I'll record on my side too, just in case. So hello, and welcome back to Programming Quantum Computers. And we're up to chapter 10. So we're actually pretty far into the book now. And this week we are talking about quantum search, which is totally not what I thought it was. So it turns out to be something cool. Now, one thing that I like about this chapter compared to the last one is there's much less math. It's mostly has to do with logic puzzles kind of a thing, which is something I used to do all the time when I was a kid. So I actually found, do a screen share here. I was just thinking like right before, I don't know what these things are called. So I had to look up on Wikipedia, and this kind of grid looks really familiar to me. Well,
Me too. I did those too. I didn't know what they were called. I love them.
So, figure out, okay, in this case, I think we're looking at how old everybody is, their favorite color, and what they like to have on their scone or something. I found that this appears to be called a zebra puzzle, according to Wikipedia. And one interesting thing is they have this listing of one that appeared in a magazine in 1962. And it has to do with who owns the zebra. And so based on what everybody smokes, whether they smoke Cools or Chesterfields or Lucky Strikes, who they live next to, you can figure out who owns the zebra. And apparently this one has two different solutions. So anyway, it's that kind of stuff. So it really kind of resonated well with me as far as like how I think I understand this. So as usual, please butt in and make this a discussion as we go. So I'm just going to kind of flip through the book a little bit until we can kind of talk about phase logic, which is something that's new. So before we talked about basic logic gates in chapter 5, and rather than going back to that chapter, because it turns out using the Kindle online isn't great because you can't have multiple windows open. They all want to be on the same page. So thank you, Kindle. So I did some screenshots instead. So we kind of saw our logic gates that were based on 1-0 values. And this was back in chapter 5. And so the kind of the not, the and, the or, the XOR, the nor, the XNOR, all of those gates are kind of pictured here. And we're actually going to use some of these. But what chapter 10 introduces is the idea of phase logic. So rather than going based on the amplitude, which is what those other gates were doing, we're doing it based on the phase. And so the example that we have here is kind of fun to look at because you have to look at which way all of the lines are going. And so the idea is, in this case, we have 2 qubits, and based on the phase, we're going to, or based on the logical operator, we're going to decide how the phases are changing. So with an OR, the first one, again, we're looking at whether the first bit is 1, or the second bit is 1, or they're both 1. So in that case, the values that satisfy that when you put them all together is 0, 1, 1, 0, and 1, 1, which are the values 1, 2, and 3. I love going back and forth between binary and and decimal here. So the values 1, 2, and 3 have their phases flipped 180 degrees. That's the gist of that. And so it goes through all of the gates, or all of the different logic gates, to show how the phases flip. And it's exactly the same way that 1s and 0s would respond when we're using amplitude. It's just the difference is now we're doing phases instead of the amplitude. And so the thing that I found interesting about this is there are also phase logic gates that correspond to this. And so this kind of shows the same thing. We have the not, the or, the nor, the and, the NAND, and the XOR. So by using these combinations, we can get we can rotate the phase 180 degrees based on the logic rather than changing the amplitude. Now, where this becomes useful is when we start looking at these various logic problems that we might come up with. So kind of the idea is we're taking several of the ideas from previous chapters and combining them. So we're getting our basic logic gates that we saw back in chapter 5. We're also looking at the phase logic, which is new in chapter 10. And then we're also looking at the Grover mirror that we saw back in, okay, I bookmarked it. I'm going to regret this. Yeah, the Grover mirror, which is back in chapter 6. And just as a reminder, what this is this is taking an amplitude and turning it, or I'm sorry, taking a phase and turning it into an amplitude so that we can actually read it. And this is when we were talking about the waves. So yeah, the idea where we had our waves and our phases were going around a certain number of times, and the Grover mirror would help us turn that phase rotation into an amplitude so that we could read a value based on how many times it goes around. So you can rewatch the YouTube video on chapter 6 for a reminder of all of that. Okay, so these are all the pieces that we're putting together, which is nice. Let's see if this takes me back. Nope. Okay. It was a lovely thought. So, so kind of the interesting thing is we're trying to figure out if a particular logic state is possible. And that's really kind of what we're looking at here. And that's an interesting way to think of something. It's like, is this problem solvable in a certain way? And so in this diagram here, we have an A, B, and C, and then you can see the little parentheses are describing what we're doing. So we're saying A, so A is true, or, so this thing in the middle is an or, not B, so this is a not gate, so we're inverting B. So we're saying if A and not B are true in this first one, and then we're doing an and with C. So then we're seeing if all of these statements are satisfied by a particular input. So kind of, let's go to the first example. Now, what I did was I relabeled a bunch of things in my versions of these problems to help make it a little more clear, because there's some things missing in these labels, and I think this registers. So for this particular one, I relabeled it a bit. Let me make this bigger. So this is the same circuit diagram, but instead of having a reg over here, I have an A, B, and C so that we can keep track of which of these qubits refers to which one. And then this label stays the same. So we want first to see if we have A or not B. And then the second statement is an and C. And this wasn't labeled in the original one, so I added an and C to the label to make this clear. So the idea of how this works is also kind of interesting because we have multiple statements. In this case, we kind of have two statements. We have the A or not B, which is actually, that's kind of two on its own because there's the not in there. And then we have the and C. And the idea is that we use the standard amplitude-based logic gates as much as we can. And then for the last operation, we use a phase gate. And then after doing that, we can uncompute everything and then do our Grover mirror to get the actual value out at the end. This particular example doesn't do the Grover mirror, but it kind of shows how this is put together. So let's just take a look at how these are put together. Not that one. Okay. With this. So here's our logic gates. I think I can make this a little bit bigger. Okay. So our first statement is A or not B. So it actually starts out with the not. So this first, this first not that we have on the B line is actually corresponds to the not that we have here. Now, the second part of this, where we have this interesting shape, is an or, and it actually corresponds to this one here. So in this case, we're using a scratch qubit. That's another thing I renamed because what was it, ancillary or something? That probably has a meaning in the quantum world, but it didn't have much of a meaning to me, so I changed it to scratch. And so in this circuit down here, this is doing an A or B, and then the result is coming out on the C, which is the scratch bit in this case. So this is doing the same thing, only it's coming out down here. So the C bit isn't being used right here. So that's the first part of our logic statement that's doing the A or not B. And then we have to do the and C. Now, rather than doing an and like we have here with the amplitude gate, we actually use the phase instead. So the phase and is the two lines connecting, which is the conditional phase. So it's a C phase, but with phase, it doesn't matter which one's the conditional, if we remember back to that. So it's not like a C naught where we have the naught and then it's pointing to what we're conditioned on. Instead, kind of both of them are equal. And so this phase and is what we have here in the middle. And so for these steps, what we're doing, and we'll actually be able to see in the circle notation how this works. So kind of the first thing we do is, so we're initializing everything to 0, and then we're doing a had on the qubits that we're operating on. So that puts us into a superposition. Then through this series of operations, again, we have kind of the not B, and then we have the set of operations that do the A or B. And then so that kind of puts our circles into a state that doesn't look very useful. But then when we do the last statement as the phase and, it flipped those phases. And now when we uncompute doing the A or not B backwards, what we end up with is we have 3 of the phases which are pointing the other way. So we've just put our A, B, and C qubits in, we've changed the phase of them without changing the amplitudes. And then by using a Grover mirror, we could read a value out of this, which is not part of this example, but we'll see that later on. Does that make sense? How am I doing so far?
Great.
So kind of once I figured out the, or once it sank in, because it's stated quite clearly, do as much as you can with the regular logic gates and then use the phase for the last one. And in our situation, the last one is always an and. But I'm kind of comforted knowing that because there's these other phase gates, if our last thing that kind of glues our logic together isn't an and, we do have other options. So that's kind of this first example here. And then we get into the fun thing, logic puzzles. And in this case, we have the kitten or the tiger. So the king has given his daughter 2 boxes, and one of them has a tiger that will eat her, and one of them has a kitten. I don't know how much this father loves his daughter, but
I
it's
wonder how many
interesting.
he went through before they finally.
Yeah, how many daughters did he have? So apparently he wanted a daughter who could solve logic problems. And so there's each of these boxes has a label on it. On box A, it says, at least one of these boxes contains a kitten. And then on box B, it says the other box contains a tiger. So another thing that I like, have you seen the movie Labyrinth? No? Labyrinth, it's a fun movie. It's like one of Jennifer Connelly's first movies. She's like 16 in it. It also has David Bowie. So, and it's the Jim Henson Company. So it's she ends up with a logic puzzle similar to this. It's, you know, the Lady of the Tiger story, where she walks up to two doors and one of them always tells the truth and one of them always lies. And so she has to figure out by asking one question, how do I know which is the good door? And she comes up with a great question. She says, would the other guy tell me that this door leads to certain death? And so if he's lying, then the other one. And if he's not lying, then the other one would be lying. So it would be the other one. So she figures it out. Go watch Labyrinth. It's worth the time. So turning this into a logic circuit, we have that down here where a kitten is a 1 and a tiger is a 0. So the first step is trying to figure out, is this possible? So is there a state that satisfies both of these statements? And by setting up this circuit, our ingenious daughter did find the kitten. Let's look at, I'm going to go to the circuit diagram on this. Let's see, does it make sense to make that one? Yeah, I can make that a little bigger. Because this actually does have a the Grover mirror and a different phase logic. So, okay. Let's review. Okay. The circuit that she came up with. So in this case, we have a not A, and then we have an A or B. So at least one box contains a kitten, A or B, and then the other box contains the tiger. So not A would tell us, yeah. And then the last piece is that both notes are true or both notes are false. And if both notes are false, that means that there's no kitten and the girl would just get eaten, I suppose. So we want to take all three of these statements and put them into our diagram. And so starting out with the A or B, okay, so one of the boxes contains a kitten, and then not A on our second step. So this box does not contain the tiger. I might have that backwards. And then the both are true or both or not true is an XNOR operation. And if we go to our phase operations, because again, our last piece has to be a phase, we have an XOR here, which shows us the basics that we have to do to get that across. And it's almost the same, except there's a not in the middle. And so that gives us the inverse of an XOR, which would be the XNOR. So complicated diagrams, but they're all there. And then the next step is to uncompute all of the standard logic and then do a Grover mirror to get the solution. And so let's just kind of step through this one to see what we do. So again, we're starting with a superposition. The A or B flips things around. The not A flips some other things around. Then when we do this phase operation, we'll see that this bit has been flipped 180 degrees. And so now when we uncompute, so here's the uncompute of the not, and then the uncompute of the or, and then if you notice the uncompute are the same three operations we have here, but in reverse order. So it is actually a mirror. And so that puts our amplitudes back where they started. But notice that our number 2-bit is now pointed the other way. And then if we do a Grover mirror on this, which will tell us, which will do the amplitude amplification, take that phase and turn it into something useful, we see that the result is in fact 2. And then I did a read at the very end. I added this so that we could see that box A, so that the set of inputs that would satisfy both of these notes would be box A has a tiger, it's a 0, and then box B has the kitten, a 1. So how's that going? Still going? So I thought that this was kind of interesting, talking about how we can start putting these logic problems together to see if they're solvable. And in this case, the other interesting thing that was noted in the book is that this is figuring this out with a single operation. So it's not like peeking in box A and then saying, okay, well, if box A has this and box B has this or that, or peeking in box B and figuring it out, or coming up with the 4 possible combinations, which again are both are tigers, both are kittens, tiger, kitten, kitten, tiger, right? So we have our 4 different options. And by using the superposition, starting out with the superposition, we can figure this out with one set of operations. So that's the part that I found is kind of cool and started me thinking about, okay, I have no idea how to use this in the real world, but it looks really useful.
Yeah, I like that. That was fun because, yeah, that last little bit of the puzzle, it's probably a little contrived, but the dad says, oh, you only get one shot.
Yeah.
And unlike the door problem, you had one question, you could solve it in one question. But with a traditional circuit diagram, you had to set your inputs and basically see, do I get a reasonable output? Can I set box A to be the tiger, box B be the kitten, run it, and do I get a reasonable result? Or are they both going to be 0? It is saying this is an invalid set of inputs. And so technically you'd have to run it at the most 4 times. And then he says, no, you only get to run it once. And I like how she kind of stated, either there's a 25% chance she guessed correctly, but if she failed, all she'd know is the one of the 4 options she chose was not a valid option. So now you have to guess. And, hopefully you don't want to guess with a daughter eating tiger. So I like the idea that, oh, no, you run this through a quantum circuit and you get to try all the options at the same time. And that's what hit home for me. So
yeah,
I'm eager to pull out a logic puzzle and figure out how to code it and run it once and see what happens.
You did a lot of refactoring on the book code. Did you share this in your repo?
Yes, I did. It is in my repo. This particular one is not refactored all that much. I don't think. Let me just look at, go back here and see what was in the book. So this one was actually pretty well done as far as the labels were concerned. For this particular one, I didn't do a whole lot of refactoring, and I was focusing on the circuit diagrams.
Mm-hmm.
So I wasn't really focusing on the code itself because these are kind of complex operations, as far as like, okay, well, we've got to not this, we have to see not with these 2 conditionals and then not everything. And so when I was looking at the code, I wasn't really focusing on how to make this easier to read, although I think it could definitely use some help. Did you do refactoring on this, Lynn? Or
I would have to look because I think I did all the chapters. So
yeah,
again, if you're watching this, we both have GitHub repos. Matt, I don't know if you have one, but where we put the refactored code that you're welcome to look at.
Yeah, the only refactoring I really did on this one is instead of calling it boxes, I labeled it box A and B.
Yeah.
It took me,
Yeah.
a good 30 seconds to remember which one the zeros and ones meant at the end.
Yeah, and the reason I didn't do a whole lot of refactoring is I focused primarily on the labels for the circuit diagram, and it'll actually be more clear in the next example. But when you have this QC naught with these 3 bits, even with everything renamed, you still kind of have to reference them this way because you're crossing registers.
Yeah.
Since you're crossing the main register and then the scratch registers. So one thing I actually did, I guess I should have pointed this out, is I did refactor the names, or I renamed, refactoring makes it sound more important than it is. I renamed the scratch bits, because this first one is really the A or B answer. So when we're saying A or B, we're sticking that answer into this one right here. And then not A can just stay on A. And then this scratch is really when we do the phase operation. And notice that this conditional is on the A or B bit and on the A bit. So that's what we're using for our final resolution. And then undoing everything puts things back the way that they were theoretically. Oh yeah, it was called Note A. I really hated that name because what is Note A? Well, I don't know what Note A means, and it's really whether it's an A or B. It's really what that is. Yes, I did change that label actually. Okay, so then there's kind of the general recipe for how to put one of these circuits together. And so I thought that this was kind of interesting. So the first is, can we take our statement and putting it into a series of logic operations? And here's an example of a big long one that's been done for the next example. So can we express it this way? And then step 2 is to represent each clause using magnitude logic. So if we go back to the kitten or the tiger, we use the magnitude logic for the A or B, and we use the magnitude logic for the not A. And then, this is actually figuring out how many scratch bits do we need. So in doing this process. So in this case, we needed a scratch bit to hold this A or B operation. And we did not need one for the not A, because that's something that we could just operate on that particular qubit and then undo it when we were done. And then we have this the scratch one that's required for the phase operation that we have at the end. So in this case, it says it's useful to have one scratch bit per logical clause. And we'll actually see that in the next example. You end up with a lot of qubits in that case. Step 3 is to initialize the QPU registers to a 0 state. And again, that was done at the very beginning of this. Step 4 is to use the magnitude logic to build each of the logic gates one by one, and then putting the outputs into scratch qubits where we need them. And so again, that's what we did with this A or B and the not A. And then once all of the clauses have been completed, perform a phase logic operation between all the scratch qubits. So this particular example kind of steps away from that, because it actually does a phase operation on the XNOR, as opposed to saying, okay, well, let's do the XNOR and then AND all of these together. But the last operation does need to be a phase operation in order for this to work. and then uncompute. So do everything backwards, and then run a mirror. So the Grover mirror operation to try to get the, to do the amplitude amplification, turn that phase into a value that we can read. And then it says, repeat this as many times as you need to get the amplitude amplification to work. So going back, depending on the type of phases that you had, there was always an optimum number of times to run this mirror operation. Sometimes it was one, and we would get a, hey, here's a solid 100% confidence answer. Sometimes we would get like an 80% confidence answer, but then if you would run the mirror again, you might get a 95% confidence answer. So that's going to go back to chapter 6 to talk about how do you find the optimum number of times to run this to get the most confident answer, I guess would be the best way to say that.
So if I were to understand this correctly, then if we were to run the mirror step 7 and get 100%, that would lead us to believe there's only one right solution to this, which most logic puzzles have. But if we weren't to get 100%, if we had that 80 and 20 or whatever, then that kind of implies there's more than one solution.
There might be more than one solution that satisfies the logic. So kind of like when I showed the zebra, zebra logic from, who smokes what cigarettes at the beginning, they actually showed there were 2 actual answers based on that logic. So it's possible that there's more than one initial state that will satisfy all of those values. So we might not end up with 100% at all. Yeah. And then for the one where, for this kitten or the tiger, we do end up with 100%. And it then, if we were to run the Grover mirror again, this is a situation where it basically puts it back. So we'd basically end up kind of back where we were. And it would kind of flip back and forth between having a good value and a useless value in this case. Do you remember that from?
Yeah. Yeah, because most logic puzzles, they're geared to have one right answer, right?
Yes.
But then in my old days doing Lisp and Prolog programming, which I'd like to get back to, you were given all these scenarios that was like math class, on stats. You have 10 students in the audience, you've got 10 candy bars, but 3 of your students are allergic to peanuts and 2 of your students don't like chocolate. How many ways can you distribute these candy bars to satisfy all the conditions? And there may be 4 ways. So I'm thinking, a normal problem might have these restrictions, and I'm trying to solve this, ideal. Well, there might actually be 4 ways to do that. So I'm wondering if we were to run our Grover often, those 4 options may kind of rise to the top. I'm not sure.
Well, I think what it ends up, if I remember correctly, is that if there were 4 correct values, you'd end up with a 25% confidence for those 4 values. And then if you did a read, it's basically luck of the draw, which one would come up. But if you ran it 1,000 times, theoretically, those 4 answers should come up about 25% of the time.
Yeah.
Oh, probabilities are fun, aren't they? So here's a big logic problem. That's this 3-sat problem. Okay, and maybe I missed it. 3-sat, what does that mean? Does that stand for something?
I think on the previous page, he called this as a general Boolean satisfiability problem. So I think maybe a 3-sat was, he's got 3 variables that he needs to satisfy some conditions. So we have A, B, and C. And it's a Boolean satisfiability problem. So you have multiple conditions. You have way more than 3 conditions. Right. I'm dealing with 3 variables.
Okay, that makes sense. I'll go with that.
Thanks.
And so that takes us to the next example, which I'll go back to my code. So this is one where I did a lot of, so these were labeled clause 1, clause 2, clause 3, and clause 4, and that's no good. So I relabeled these in mine. And I also renamed these to scratch 1, scratch 2, scratch 3, and scratch 4 so that we could keep track of those. I actually did try to rename the registers to A, B, and C, but that made a lot of problems because there's certain things that kind of are better when they stick together as a register with the other operations. I think I actually had trouble with the Grover at the end when I tried to split them up. But let's take a look at this one to see if we can figure it out. So I'm going to assume all of these clauses at the top are correct and actually match what's in the book. Are those big enough? Can you see those?
Yep.
Okay. Oh, actually, I came prepared. There. Okay. So I'm going to put this side by side with this so that we can kind of look at what we're doing. So again, the first step is to initialize everything to zeros, and then we put our register into the superposition for the A, B, and C. And then we just kind of go step by step for each of these clauses. So the first one is A or B. So again, we kind of have this or that we saw in our previous two examples. And this is going into the scratch 1. So we're doing that same operation with the scratch 1 holding that answer. And then we have not A or C. And so the not operation is actually associated with the A. So this first, I might get brave and draw. This might be a bad idea. Okay, so this is the not A, and then the or, the A or C is this middle part, and that looks again a lot like the ors that we've already seen with going into the scratch 2 for the answer in this case. Now, the thing that I was curious about was this not that we had on the at the end of this, because when we looked at the previous example, oh, that's nice. My squares are still there. Oh, I'm still drawing. Okay. Stop drawing. Okay. So when we went back to our first example where it said A or not B, we did the not on the B and then the or, but we didn't undo the not. And so I was a little confused by this at first. And so I actually tried taking out this second not to see what would happen. And it breaks everything. So what I found is that the reason why this is important is because we basically changed the A register by knotting it. And so we want to unknot it to put it back into its original state before we continue computing. The reason why we got away with it in this other example is because we didn't use B for any other operations. So we knotted B here. We didn't have to unknot it because it wasn't used anywhere in the middle. And then when we got to the uncompute, it's just put it back to its original state. So because we weren't using reusing B, it wasn't important to put that knot back. But in this case, since we are reusing A in this case, further down, this A or C, we need to put it back. Does that make sense? Because I had to stare at that for a really long time to figure that out. And then the next one is a not B or not C. So again, we have the not B, not C to start with. We have the or in the middle, and then we have the not B, not C undoing that not at the end. And then the last one is an A or C. And so we're putting the answers into the scratch 1, 2, 3, and 4 respectively. And so since we have all of that, then at the very end, we can do this thing that's referred to as the flipped phase, where we're changing the phase around, where we're doing a phase and on all of our scratch bits. So all of the things that we've computed so far. And again, the phase and is this one. And so we're just doing this across all 4 of these. And then the uncompute is doing everything again backwards. So I'm not going to click all the way through this, but we'll kind of click up to here. Oh, that's right. There's too many circles on this one. Let's click back here. Okay. So the idea is we go through everything. Oh, actually, let me start here. So at the beginning, we have the superposition where it's spread evenly across these 8 values. Phase is all pointed in the same direction. When we do our logic and our phase flip and then put everything back where it belongs, now we'll see that one of these is flipped around. So on bit 5, qubit 5, it's pointed the other way. And so if we do a Grover mirror at this point with the amplitude amplification, it comes out almost 100% to be a 5 value. Now, one thing that I added to these circuits was I added a read at the end, just because I was kind of curious. In this case, it comes out, A is true, B is false, A is true would satisfy this particular logic. And I was curious, but if we run it multiple times, you'll see that sometimes other values come up. So our Grover isn't 100% confident in this. And I think since we're so close to, again, we're like, this is the vast majority of what we're expecting to get out. And so if we're, again, to run this 1,000 times, we would see probably, okay, I'm really bad at estimation. I would say 90% of the time, 5 would be the answer. Does that sound like a reasonable estimation based on the circles that we're looking at?
Well, and the gotcha here is, remember, we're seeing the magnitude is the square. So it may be less than 90%. But if 50% of the time it hits a 5, and the other 50% of the time it's spread across these minuscule values of the other ones, then that 5 would still peak out.
Yeah.
I just like circle notation only because if you do dashboard design and you look at the, usability of dashboards, they'll say all the time, representing a value in an area of a circle is one of the worst things to do, because that area in those outer circles have quite a bit of space in them compared to the inner part of the circle. So you could have a circle that looks to be 90% filled and really it's only 60%. It's just hard for a human to intuitively read the area of a filled circle.
Okay, I know a situation that's relevant to real life, and that is the size of a pizza. Because people compute what is the area difference between a medium pizza and a large pizza. Even though the large only looks like it's this much bigger than the medium. So I'm totally with you there.
It's exactly right. Yeah. That's fine.
Yes.
However, I'm going to just jump in because I've been working in environments that do not have the circles, as I was showing Jeremy earlier today. And as imperfect as they are, I'm happy to have them, because when you have ASCII art for most of the other output, the circles are looking pretty good. When the options are ASCII art or block spheres, which they're too precise in a lot of ways for me, because there's too much information when you try to have a 3D sphere. I get what you're saying, but just do some of the other output where you see the ASCII art. You'll like the circles better.
And not to dive off that area, but of course, just like programming or designing anything else usable, what is the intent? And so, using notations that quickly communicate the intent. Yeah.
Yeah, I mean, it's a hard problem that they've moved the needle, but it's not solved still. You know, one of the areas that I look at for learning calculus, for example, is the YouTube channel 3 Blue 1 Brown, Grant Sanderson, who basically full-time makes animations of calculus on up because it's non-trivial to do this. And the fact that we have anything at all, like I said, when I was working with other libraries from the other vendors who are commercial vendors and their output is ASCII art, I was like, yeah, as imperfect as the circle notation is, I'll take it.
Yeah, totally.
I'll take it.
So the last example that we have is showing an unsatisfiable 3-sat problem. And if you look closely at the circuit, or I'm sorry, the logic, it's actually exactly the same, except they add an and B at the end. So that's the only difference in the circuit. So rather than going through the entire thing again, all of these clauses are the same. And the scratch bits are the same. The only thing that's different in the circuit is for this and that was just anding the scratch bits together in the previous example, it's adding the B. And so by doing that, apparently we create an unsatisfiable problem. So again, kind of if we look through this, after our put things into superposition, we have kind of the spread of all of our possibilities. And then running through the circles again, we kind of have too many to show on the screen in this environment. Unfortunately, making this part bigger or smaller, I think just kind of makes it worse. Kind of hard to see what's going on. And then the phase flip, actually, yeah, if you look really close, squint, it doesn't flip anything. So as I go back and forth across this phase flip, the circle diagram is unchanged. And so what that means is that as we uncompute this, our phases are going to end up exactly where they were before. So this is an unsatisfiable problem. And doing a Grover mirror does us absolutely no good because it flips all of the phases. And then doing a read on this, as you can imagine, will give us just a different value each time. These are equally likely to come up. So there isn't a state that actually satisfies all of these conditions. So I think that's also kind of interesting that we could figure that out. And I'm glad that it's just, I thought it was, when I first saw this, I thought it was a completely different circuit. And when I noticed it was just, oh, the and B at the very end, that made me happy because I already had done through the digging of the first part of the circuit. So that made me happy. And so, yeah, it's interesting because now that amplitude amplification doesn't really get us anywhere. Okay, and then now's the part where I would like some interaction because the algorithm speed up, I kind of have a general idea, but it's also kind of nebulous to me. So I'm assuming that if we have these logic problems in conventional algorithms where, again, we might have to say, okay, well, I've got 3 values and I need to stick in 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. I'm not going to keep going, but all of the values, 8 different values, and then run it through to see if any one of these satisfies all of these conditions. Being able to do that with one circuit definitely, I see, has optimization enhancements to it. But as far as the big O notation, I'm kind of rough on big O notation. I have kind of the general of, what is it? Exponents are bad. Square roots are good. Multiplication is usually ignored. But that's about my extent as far as big O notation is concerned. Any?
Well, I mean, I don't really know more than you, but I just noticed in the book there, it says to obtain a QPU speedup, combine them with the quantum routine. We simply need to substitute the repeated probabilistic subroutine with an amplitude amplification step. So to me, even though I don't have any more knowledge than you do of the underlying math, what that says is, if you want to speed it up, take one method of solving this one portion out and put this other method in. One of the things that I might be appropriate to bring up here to share with the group is there was an Azure Fridays webcast that I dropped into the Slack. It's Scott Hanselman interviewing one of the co-authors of the book, Mercedes, the woman who wrote the Q Sharp stuff. And she did an excellent job talking about the life cycle of quantum programming. And in particular, she clarified for me why you would use a local simulator and then a cloud simulator and then run on a cloud QPU. And she talked about addressing this type of challenge where you would have an environment that could be deterministic. Very specifically, if you set up your problem with a 0 shot run, which was new to me, rather than the default of 1,000 shots, you can then put in basically the equivalent of console log statements in a local simulator so that you can verify if you make this substitution that you're getting the result. So in other words, you can read, it's an observable. So I thought that was really fascinating, and it really, really was helping me to understand what you would do exactly to figure this out. So the TLDR is, in the local simulator, you can actually test it to see. And that was very interesting to me. Like how you exactly do this, I think I could figure it out because I know what amplitude amplification is. But to me, the more important aspect of this is like how you would actually test it. And what I learned from watching that presentation is running on a local simulator, because all of the cloud implementations include local simulators and cloud simulators. And I couldn't understand the difference before that. So I don't know if that's helpful, but it was helpful to me.
So is QC Engine considered a local simulator because we're running it on our local machine? I didn't get the distinction.
Kind of. I mean, it's not that the point is it's not it's a library. It's a learning library. So it doesn't include all the features of a local simulator, which was kind of the big takeaway for me. Like this idea of 0 shots and observables. I was like, because as you'll see in subsequent chapters that have both a classical and a quantum implementation, what I did is I pulled it down to Visual Studio and I replaced the QC print with console logs on the classical. And it was interesting because I was like, oh, if you have a SDK with a local simulator, you can you can do that while staying in the quantum environment, but it operates as if it were classical. So you have tools. You can debug, for example, when you're in the local environment. I know. So I thought that was, to me, that was a very big revelation, because we've had a lot of questions from the group over the course of learning on how you optimize. I mean, because that's kind of the point, right? Another thing that was in that presentation is she worked with a Jupyter notebook, was interesting, Python that called Q Sharp, that would estimate how many incidences of the types of gates. Because another thing I learned is that the cloud QPU implementations support different kind of gates. And we kind of saw that with IBM, where like Hadamards would be decomposed into other things. But like, for example, if you're on Amazon, you have INQ or you have D-Wave or you have Rigetti for QPUs. And they cost different prices and they support different types of gates. So again, when you're working locally, what you can do is you can use these estimators. It's almost like a database query planner in a way, like with the operations. And you can see which gates and how many gates. So in this, to address this particular situation we're looking at, and she shows this in her demonstration, she starts with a complex equation and she says, oh, this would be too costly to run on an actual QPU. because of the number of CNOTs that are being run here.
Mhm.
So what I'm going to do is I'm going to simplify this, and I'm just going to focus on, the sort of concept would be the quantum part, the all possible, if you will. I'm going to take everything else off to reduce the number of CNOTs so that I can run it. And she said, as this evolves, this kind of refactoring to quantum only will be done automatically by the vendors. But for right now, you use these tools. You start with the local simulator, and then you can run Cloud Simulator to see what the implementation would be on the various vendor QPUs before you run it. Because again, it's really expensive to actually run. So you want to have like the business justification. I'd really recommend anybody watching this to, like I said, I put the link in the Slack, or it's Azure Fridays with Hanselman. It was really, really good because she did it end to end. What was interesting though, is the more I get into this, I'm not, I wouldn't probably use Q# as my first language because it's more C# like or C like, whereas I'm preferring Python libraries. So yeah, I've been really looking at the tool chains because in the chapter coming up that I'll be presenting, there's different ways of presenting a pretty complex algorithm, and I'm trying to look at the different tool chains to understand it and be able to present it better. So I think we're at a good stopping point. Jeremy, did you have anything else?
No, that's actually the end of the chapter.
Okay, so Matt, did you have anything else on this chapter?
No.
Okay, so I'm going to go ahead and stop the recording.